Okay, are we on?
Yeah, I don't know if you need to accept that the recording started.
Didn't ask me. That was interesting. Oh yeah, something.
That's your background.
Okay.
What place is that?
I think it's Hawaii. All right. Is everything back to normal?
Yeah.
Okay. Okay, recording is on. Hi, folks. Hi to everyone online. I think we were already connected to the folks online. We're almost on time. I think everything should be working. Okay, so welcome to the Halloween edition of our meetup. I don't know if you actually read the intro for the event. Uh, I'm not that good with the limericks and poetry. I actually asked ChatGPT to generate this for me, uh, and the prompt I used was write me a short poem about why Asan is important for memory safety in the style of Dr. Seuss with a Halloween theme. So that's how I got the intro for today's evening. Anyway, so let's start with the scary bits for this spooky Halloween event. And scary bits is that uh, this is just one of the vulnerability reports out there. Uh, the one that I quickly got access to, uh, but pretty much they all look the same. Uh, Small variations on the order and the frequency impact of each kind of vulnerability. We can quickly see that most of the common vulnerabilities that are encountered in these kinds of safety surveys that are run across the industries, um, these are both independent studies as well as studies done by individual companies. Um, each company usually surveys their niche, and more or less we see these kinds of issues. So in general, memory safety issues continue to dominate common vulnerabilities exposures. So they're trending year over year, and they're somewhere between 70-75% of all vulnerability exploits out there. So this is a major concern, and documents like the recent NIST paper or the Consumer Reports paper on the NSA report and so on are just alarm bells for the existing studies that have been run for years on these kinds of vulnerabilities that affect software. And there's also kinds of opportunistic exploits. I listed a bunch of popular techniques of exploiting memory safety errors. Return-oriented programming, this was a very popular one for the past 10-15 years now. By the way, it's ROP is actually Turing complete. You can actually run, there's tooling that can generate programs using rope trampolines and so on. So it's very cool. If you want to learn more about these kinds of tricks, there's very good presentations out there, both Black Hat and in our conference community. I would recommend presentations by Jim Radigan from Microsoft, and presentations by Patricia Ass um, on these kinds of exploits. And generally, our attitude has been that we are pretty much okay with it. And sometimes we would just patch them. Like usually you have reports, security bulletins, issues, we patch them. There's usually some kind of escalation or um, let's say either bug hunts or in bulk efforts to address a bunch of long lists of reported vulnerabilities. And the general approach is we have the thing, we address it, we patch it, we isolate the problem, and we move on. And that's about it with our approach. But there's a lot of tooling that has been built to assist with this. So I listed here just a couple of them. They tend to lean a bit more heavy on the Windows side because I know more about these than others, but many of these kinds of things are platform agnostic. And some of the efforts that originated on Windows, for example, have been tried in other places and the other way around. So we have multiple ways of addressing these kinds of issues, either by enriching the source code by using source code annotations to give better hints to tooling around lifetimes and semantics of references and arguments into functions, what's input, what's output, what's input, and so on, all sorts of annotations at source level. You have your set of hardening tools and techniques for binaries, for code gen. So there's multiple technologies for secure code generation. I listed a bunch of them. Those there, where and this is, by the way, all these areas are areas of active development. I'm not presenting them in any particular order or historical order. They're all active areas. So both code hardening efforts and secure code gen and source annotations using custom attributes and so on is in heavy use in many code bases, including Windows or Chromium and a lot of big projects. Static analysis and dynamic analysis, again, a bunch of good tooling out there in multiple tool chains, both in GCC, Clang, MSVC, and so on. And the idea is that we need all. It's not like one is a superior method. Each one has its strengths and weaknesses, and we kind of need all of them combined to get some confidence that the code we generate is memory safe. And I'm not even going to mention TUB and other stuff. So I'm going to focus, as the title implied, I'm going to focus on dynamic memory analysis. But before that, I want to briefly do a quick primer between static analysis and dynamic analysis. And I think it's important to make this distinction, just in case not everyone is familiar with these kinds of tools and techniques, and maybe disambiguate some of the strengths and what the tools can actually do. So static analysis, it's usually done offline. It's not in the normal compilation cycle. You usually need to use another tool. It's not the job of the compiler to do this, although most of compiler tool sets actually provide static analysis in the box, but it's not part of the usual compilation cycle because it's usually more expensive to run these kinds of analysis. Usually this kind of analysis is intimately linked to the programming language we use. So it's very different if we're doing this for C++ or if we're doing this for Objective-C or Swift, or it really matters. The programming language is very important. The tooling needs to have a proper understanding of the programming language. And that's because it can detect a lot of semantic issues, of course. It's not perfect. It can yield a lot of false positive results. Sometimes you waste a lot of time on a wild goose chase, and it's not always obvious that it's a false positive. Some scenarios are fairly difficult to identify. It's generally poor at whole program analysis. Um, these kinds of tools usually focus on a per translation unit basis, and it's very hard to do anything fancier than that to track things across different TUs. It's almost helpless around virtual functions um, for obvious reasons, because these kinds of bindings are not known at compilation time. And of course, around global pointers, the analysis is much more difficult. And if we're talking about pointer aliasing, it's very, very hard sometimes to prove things about aliasing relations and to track lifetimes appropriately.
Hard problem is a specific mathematical term. Do you mean that one or just that it's difficult?
Which
Well,
I didn't hear the beginning, sorry.
if something is a hard problem, that means that well, in mathematics that it cannot always, that there is no algorithm to find the solution to the problem. Possibly there may not be a solution to the problem, blah blah blah.
Yeah. So
Was this exactly what you meant, or just that it's a complicated?
I think it's unsolvable. Yeah, I need to repeat the question. Sorry. The question was in the bullet point when I said it's a hard problem. Is it hard in mathematical terms that it's not solvable, or is it hard in terms of is it hard?
Is the last direct LS analysis is hard?
Yeah, that's what I meant. So or is it hard in terms of engineering? Like it's difficult to get it right. It's the way the language is specified and what's allowed and what's legal C++, it's impossible to solve. It's not a matter of, oh, tooling will get there. It's like the halting problem. It's impossible to solve all cases just because of what C++ allows you to do. But we don't have to solve it. I would contend that its perfection is the enemy of getting stuff done. We can go way beyond the status quo of what can be done. Doesn't matter if it will never be perfect, or if it will never have perfect guarantees. If you want guarantees, then you have to restrict what you can do with the language. So you will need to subset what you can do. So you need to impose artificial restrictions over what's legal today in the language. But we can do a lot more. So the tooling can do a lot more. And the way we help tooling is with, I mentioned this in our last meetup when I talked about lifetime bound attribute and lifetime analysis. And I do recommend, if you're interested in this kind of thing, to watch Gabor Horvat's presentation from CPPCon this year when it comes online. It's not online yet. It went into detail in these kinds of issues. So advances have been made in tooling in this area, but we can do a lot more. But sometimes we need to help with these kinds of annotations. And there are other efforts, speaking of trying to build a more robust thing, efforts like Sean Baxter is doing in Circle, if you're familiar with the Circle compiler, where he's trying to implement Rust-like borrow checking in C++, but that's a sort of a C++ fork. It's no longer standard C++, but it's an interesting effort. And by the way, you can play with it because it's in Compiler Explorer. So you don't have to go to the struggle of building it yourself. So Circle is an interesting effort, but it's no longer C++. It's a flavor.
But there is still a hope that it will be like Boost or standard library. They'll just figure out something that actually works and is well usable, and it may serve as an inspiration for the next standard.
I like that you're optimistic. It's good that young people are optimistic. Yeah, I'm not trying to deride the project. It's a great effort, and we can learn a lot from it. But I'm not as optimistic that the standard C++ language and community and so on are gonna align here.
They have been doing a lot of crazy shit everywhere, and like I understand that most of that has no chance of ever getting to the standard, but they have a chance to experiment with something.
Experimentation is good.
And
Yeah.
they might come up to something with and this might lead to some idea that could be taken into C++.
Somebody joked, I don't remember where I heard this, at one of the conferences this year. Somebody joked that we should all just throw away all the compilers and just all get behind Circle and that's it. Uh, uh, it's sure it's a nice dream, but
There's too many features now. Many of them are, in my opinion, just crazy stuff that could be done better, probably.
yes, if you let go of the past, things become easier.
No, I mean it's not like related to the past. It's like we just have this problem. We come up with this solution, and it solves our problem. But like if they add something new to C++, if you have something that's like being checked that yes, it's usable for so many different problems and use cases. And even if they accept it, there are often various defects. And if it's something they need to circle, this is probably like
That's
not very well overthought.
I cannot possibly summarize that for the online audience. But what I'll say is that I think you have something there, and what I've seen more often than not is that we're trying to figure out the most general solution to solve all problems. Like we're avoiding finding a fix for a problem. And I'm speaking not necessarily about this thing here, but we're in C++. We're trying to find the most general setting and the most general solution for a problem, rather than be pragmatic. And then sometimes that derails things enormously and overcomplicates things, because we're trying to build like the universal solution, like the grand unifying theory of. Yeah.
Well, but it's just as much. But on the other hand, you can do so much.
You can come here and scream into this. I don't know how sensitive the mic is. Maybe people can hear it. It's not a big room.
There is also a question on you need to turn it on.
Well, I cannot see the questions. If you'll need to tell me.
I've turned it on. Is it blinking? It blinked once. It's blinking. It's blinking. Okay. But not into my eyes, into my hand.
So
you can go on now. Yeah. I lost my train of thought. I was just
keep it handy.
I think that like
I have a feeling you might need it again.
Being general enough, in my opinion, like as general as possible, is often quite useful for the purpose of like future proofing it, because many things were designed long ago and can still be quite useful. While well, in case of coroutines, it's clearly something that's super universal, but you still have problems with allocation actually.
Yeah.
And it's like not sure how to.
I don't want to go on a discussion on generators and yeah.
I actually disagree with both of you on different points, but let's derail this and continue.
But I want to have that discussion. Yeah, but yeah, we can do that later over beer maybe.
And the online question is actually related to this.
We don't have to stick to a format here, like.
True. So the question is, isn't Rust lifetime a Node C implementation? Maybe it can be used with compiler extension at least.
That's why I mentioned Circle. So Circle is actually trying to do the exact same thing, to retrofit the Rust borrow checking model on C++ syntax in a custom compiler. Circle is a custom compiler, but it's no longer standard C++ at that point. So it's sort of like a compiler extension. You can think of it as.
Well, the question is like with this, I haven't been looking into that, but that's like, can can you use it without like becoming overly restrictive with C++, like no longer being capable of using object-oriented programming?
No, it's not it's not that restrictive. No.
So like they can do it without as many restrictions as
It's
Rust
it,
has, and
it's not from what I know, it's not a restrictive environment. But when I say it's restricted, it cannot allow everything that is allowed today, and it's
yeah, of
valid
course,
C++.
but, like, if you the usual stuff you need to do without spaghettifying your code, I assume that you can do that still.
Again, exactly. What's the usual stuff? And I can go on a tangent on C++ editions and why we don't have editions or epochs or whatever you want to call them, and why some people would want to fork the language and others cannot, and so on.
About this project, can you send the link to this to Discord or something?
Sure, sure.
I'm really curious about
Yeah,
it,
sure,
like,
sure.
I wonder if this could be like done with this.
You can even play. You can even play with it. It's usually there's like a fairly recent build of Circle on Compiler Explorer.
I mean, but now this just quick question: can you sort of is it done through the annotations that are used since C++17, like you sometimes slightly, unlikely, and maybe
Attributes, you mean attributes?
Yeah, attributes.
It's not like that.
It's so it's not something that would be compiled
So
by other compilers.
with attributes, that's the SAL approach that I mentioned earlier. The SAL approach, as I mentioned earlier, that's attribute based, and there are many projects that use that kind of thing for lifetime tracking. And there's Clang lifetime bound, there's MSVC lifetime bound for that kind of thing, and many other specific. For example, Chromium has a whole bunch of their own stuff for this kind of thing.
So I guess you will get to that later.
Not today. But I'm happy to talk about it.
I'll stop interrupting.
It's that's not part of dynamic analysis. It's part of static analysis, and I'm just covering dynamic analysis today. But I'm happy to chat about it. So where were we? Okay, dynamic analysis. um, dynamic analysis is sometimes intrusive. Most of the time, is intrusive. You need to compile the program in a special mode to get this. It has runtime overhead, I mean performance impact, and depending on the kind of tool you're using here, it can be from 2x up to 10x slower, and more.
And a lot more.
And more, yeah. And it depends. Here, there's all sorts of restrictions. There are many classes of programs that cannot afford these kinds of instrumentation because if you're doing real-time things, if you're doing games, graphic renderings, sensitive stuff where you cannot afford, or you're doing high-speed I/O or things where you cannot afford this kind of instrumentation, then tough luck.
Honestly, I was doing a game. I was able to run it in Valkyrie.
You did? What frame rate were you seeing? Like, it was it GIF like?
Yeah, it was horrible, but I was able to debug.
Well, Valgrind is slow. It's one of the slowest tools you can possibly use for this thing. But
it was like 50 times slower, but still, I was able to find the bug there. So it's not.
Yeah. If the bug is not sensitive to timing, if the bug is sensitive to timing, then you're gonna mask it by slowing down the process. So it depends on the nature of the bug. But in general, memory vulnerability kind of things, they're not always sensitive to timing. So yeah. So it is a restriction. So not all programs can afford to run this kind of runtime overhead. It does consume more memory. Yeah, do you agree?
Huge virtual memory allocations usually. This is a problem on some platforms.
It's platform dependent and tool dependent. And yeah, it does come with overhead because all these kinds of things need to have a side location to store stuff. And I'm going to show how Asan works behind the scenes. and then you're going to figure out why it needs extra memory. And it can be even twice the memory payload needed for the application. It's sometimes difficult to map error reports to source code, especially for release builds, for obvious reasons, optimized builds, inline functions, and so on, omitted symbols, and other things that people like to do for release builds. So it's here, I would say it's no different than debugging release builds, but tooling is improving in this area. You're gonna hear more things coming in this area in fairly soon. Some tools need to recompile the whole program in instrumented mode. Not all kinds of sanitizers need this. Some sanitizers need to recompile the whole program. Some sanitizers can mix and match. So you can compile just parts of your source code in with the sanitizer, and you can link with parts that are not compiled in this mode.
The whole program, what does that mean? Does it mean also all dynamical linked libraries?
Exactly. Yeah. 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 So depending on the kind of sanitizer you're using, you might need to recompile the world, basically everything you're using.
So,
but for other sanitizer, you don't need to.
They cannot recompile the kernel.
There's limits in what these kinds of tools can actually do. These kinds of tools usually hook either system calls or kernel functions, or they do some kind of instrumentation, and there's limitations in what they can do. So you don't need to actually reach that low of a layer. And again, depending on the tool, so a lot of sanitizers actually need to recompile everything, but not all of them. I'm going to talk more about that later. You have to integrate runtime analysis with test units. So this doesn't work by magic. Being dynamic analysis, you actually have to exercise the program. For static analysis, the tool can actually inspect, or control flow can inspect the source code, can figure out all parts of the program, even parts that you're not actually exercising at runtime. You might have dead code in your project, and a static analyzer will find issues in dead code that you're never gonna get to invoke. Whereas with dynamic analysis, you have to exercise that code. If you don't exercise those code paths, you will not uncover problems with the dynamic analysis with any kind of sanitizer. So you have to have test units, or you need to run the program through a lot of code paths. And for that, you need to have good code coverage when you're testing, either through test units or manually or whatever. You have to run those. You have to light up that code. And of course, the biggest impact comes here, and the bigger payoffs come when you actually combine this with fuzzing. More on that later.
Maybe again a little bit of topic, but with fuzzing, are there some fuzzing tools that actually can check if you can go like exploit an integer overflow to go just a little bit before the start of your array? Because pretty much that's how you get to return-oriented programming, that you go just before the start of an array.
That's just one type of problem.
But this is like a very obvious way that you just put a very large integer that's very close to into the max for the given size. Yeah. And basically, you create a negative number somewhere where you didn't expect it, and
exploit wraparounds, exploit overflows, and sure, that's just one class of things.
But I just wonder, like, can fuzzing do this? Like, very specific.
Fuzzing will. First of all, there's many libraries and tools out there for fuzzing, and fuzzing will generate pseudo-random inputs for your program. So it will start from legal inputs for your functions, for your program, for whatever, and then it will generate slight deviations and modifications of that input and run the tests that you're exercising. And they're meant to generate so many variations of that input that they will uncover input and they will light up code paths and situations in your code that you didn't think about it when you did proper unit tests. Just because of the sheer amount of input variation that they can generate, and you cannot do that when you write unit tests yourself. And yeah, they will touch things like we mentioned, like
All right.
edge cases with integer ranges and so on.
I was just wondering if edge cases can be hit with random input. That was just.
It's not really random.
Okay.
Fuzzers have strategies of how they generate that input. It's not really random. I said pseudo random.
Okay, that's just what I was.
They just don't flip bits like randomly.
Mhm.
They have strategies and how they generate inputs based on different kinds of seeds and legal values and types of input. So they're fairly smart. Not that smart, but fairly smart. And you would be surprised how many things you can actually uncover. Like it's not really sophisticated technology, but you can get a lot out of it. Like the big problem is not that it's not good technology. The problem is that people are not using it. Like if you would use it, you'd be surprised how many things you would find. I forgot to stress the most. I forget to stress the most important thing is that with dynamic analysis, there are no false positives. Like if there's a false positive, it's a bug in the tool, and rarely there's like rare situation when there's a bug in the tool. So in general, when one of the sanitizers uncovers something, you might not figure out what's going on. Like it might not be obvious. You might think it's stupid, like it doesn't do the right thing. It's usually a problem, but you just cannot see it yet. You need to spend more time to understand it. So sanitizers. So there's lots of types of sanitizers, and for the expositional reasons, for when I started with the common vulnerabilities, I'm going to focus on address sanitizer mostly today. So it's the de facto standard for memory safety issues. It's important to prove correctness of your code, not just find vulnerabilities, but people usually use it mostly to find vulnerabilities. Again, I couldn't help myself. Why did the programmer use Asan to address all the bugs? This is a joke by ChatGPT again. Honestly, it's not mine. Okay, so the kinds of things that address sanitizers can find, the usual stuff. And if you paid close attention, it's usually the kind of stuff you saw in the first table that I started with on the very first slide with the vulnerability report. So the typical suspects used after free, dangling references, stack overflows, um, memory leaks, use after return, the usual suspects. It started in LLVM by a team at Google a long time ago, and it quickly took off as the industry standard, and lots of people have been contributing to this. Just so you were aware, it's available in all major tool vendors. These are the starting versions for all of them. If you want to read for, like, explore all these kinds of types that Asan can uncover, if you're not familiar just by their names, I put a link there. You can browse each and every one and read about them. Details. I'm going to skip this one. There's all sorts of configurations, knobs that you can tinker with. Okay, so let's get more into usage and get a chance to understand how it works. So again, something fairly obvious here, where we're referencing an invalid location. If you're using an IDE, this is the kind of experiences you would see. if you're using Asan from command line tool on any platform, this is the kind of thing you will see. You will get a stack trace, and you will see some kind of memory layout with the legend. I'm going to explain what those things mean. And I would say if you are on Windows and you're using Visual Studio, I would strongly encourage you to actually leverage snapshot files. They help a lot in investigating these kinds of issues, and not just ASAN. Snapshot files are very useful to examine mini dump files and get repros from any other machine. Either you get it from a CI build, or you get it from a colleague, get a dump file, and it's very easy to open it in Visual Studio and examine it. And I would say it's a productivity boost. So it's very helpful even outside of ASAN. So in general, debugging stuff and leveraging mini dump files. And when you have an ASAN fault detected like this, it usually comes with this kind of mini dump that you can open inline in Visual Studio and see the call stacks, see the memory and so on. So it really helps in terms of productivity. You can see I have a snapshot here, an example. So this would be the kind of raw console-like output that you would see. You can do the job with that kind of thing, but you need to sort of understand how it works and what those things mean. Whereas with the graphical interface, you have a cleaner way of examining local state, examining the call stack, and tying it all with the source code. So it's just a productivity boost. But it's using an IDE not required. So you can use ASAN on any platform. You can use it from command line. You can examine those dumps in text mode. So all the information is there. And I'm going to show you how to read that information. But first, let's see how it works. So ASAN sort of works like malware. I said that this kind of instrumentation requires that you compile your code in a special way, and the compiler has instrumentation code. It does stuff to stack layout. It adds a bunch of calls into a special runtime. It's called the ASAN runtime. It adds a bunch of metadata in the object file to be used at runtime and so on. And of course, it does all the magic with memory. It detects these kinds of access patterns by hooking the usual suspects like malloc, memset, memcopy, string copy, and a bunch of other allocation APIs, depending on the platform you're compiling for. So again, mind you, you mentioned earlier about do I have to recompile everything? No, you don't have to recompile. For ASAN, this is the kind of instrumentation where you don't actually need to recompile the world to get something meaningful out of it. And in terms of what it can hook, it will never hook all the memory allocation APIs. So there's very low level system APIs that allocate page memory and so on that ASAN will not hook because itself it needs to deal with memory, and there's some levels like down where it will stop. It will not redirect all APIs, but it will redirect all the APIs that an application would use. What else? Yeah, it does error analysis and reporting. Does not require, I said that already. It's good for interop, so you can do gradual things with ASAN. You can compile with ASAN just parts of your project and examine those, and you can link everything and it will just work. Zero false positive I already mentioned. So hooking, just like a very simplified idea. I think you kind of guessed how it works. For example, if we take malloc, instead of actually jumping in the malloc implementation, it will do a jump into a special ASAN runtime implementation of malloc. It will do the setup it needs for this in the runtime, and then it will just jump back to the actual implementation. So it's a classical detour pattern. I showed this console output there. So you have the classic call stack when you get this kind of report, and you get a bunch of memory-like things where you get to see, okay, you get to see some memory around the problem. So I color-coded this. Of course, in a console, you won't see it as pretty, but I color-coded it so it's easier for you to track now. So you will see it will point you to the location of the detected fault, and all these mumbo jumbo things, FA, they have meaning. So they're different kinds of bit patterns that the Asan runtime uses to place in memory to detect all kinds of types of memory illegal memory access patterns. I'm going to show a bunch of examples, and you figure it out. So let's see what this legend looks like. So you saw earlier FA. So FA means heap left zone. So you have all sorts of stack flags, global red zone, array cookies, and all sorts of markers that the runtime will use to place in memory, and so that when it detects an access into that location, it can tell you what kind of illegal access pattern happened and in what kind of context. Where was that access? I'll show an example immediately. So this is the shadow byte legend and the markers. By the way, you don't have to remember these, of course. They will be printed in the huge console output that you'll get in the report. So you don't need to remember them. So how does it work? So if you have the technique used here is shadow mapping, where the runtime will use a site. That's why I said it needs extra memory to do this. It will use what is called shadow memory to map cleverly to map locations in your process memory. But it will not shadow map byte to byte. It's more frugal than that. So it will map from 8 bytes in process memory to 1 byte in shadow memory. So what it will do is that around your regular allocations, it will actually poison the memory. That's the terminology that's used, poisoning memory. And this is where those regions that I showed earlier, these kinds of regions are useful, because it will use different kinds of flags to poison the memory around your allocations, depending on the kinds of allocations that are required. If you're using the stack, if you're using the heap, what kinds, if you're at the boundary, like at the beginning of the stack, in the middle of the stack, at the end of the stack, if in what parts of memory are you allocating, and it will flag the shadow memory accordingly. So these red things will be filled with these kinds of things, depending on where you are, what kind of memory access you're doing. So this is, and it, as you can see, it constructs a boundary. The red thing, you see the red zones, it constructs a boundary around legal memory locations. And the reason it does that, it's so that it detects when you're accessing things in the red zones. So the whole purpose of the Asan runtime is to poison illegal areas and then detect on each memory access, detect an access in the red zones, in poison memory. And how does it do that? Of course, a simplified version here. Let's say I'm dereferencing a pointer P here, and I have bad food here. And conceptually, what it does is it checks if that address is bad in that shadow memory. So it says if P is bad, then I'm going to generate a report in Asan, in the Asan runtime, and I'm going to crash the application so that you don't get to that memory access. So each time you actually want to write to this location, before any write, the runtime inserts an indirection, a check like this, so that it prevents the write and reports the memory location and the kind, based on the kind of flag it sees there in the red zone, it will locate the kind of illegal access that it detected. And this instruction will never be reached. More on that later. So I put an asterisk there. So by default, if a shadow byte is poisoned, Asan runtime reports and crashes your application, so it doesn't zombie limp around. So the idea is to not let the application do an illegal access that can be exploited. So that's the thing you don't want to do. You don't want to reach the situation where you get the illegal write that can be exploited. So there is such a thing, continue on error, that I'm going to talk about in a few slides. So how does it work? It needs to do a lot of lookups into shadow memory. And these lookups need to be very fast because, as you figured out, for any kind of writes that we're doing, the compiler generated those checks that it inserts before each such access. So lookups into shadow memory need to be very fast. And it's sort of maintains a lookup table for every 8 bytes in user memory are tracked by a shadow byte in shadow memory. So it sort of uses an eighth of the address space there. And a very basic calculation I showed here an example just to see that this kind of lookup is not something complicated. It's just a matter of some arithmetic operation here where you use the user address, do a shift, add some offset, and get the and write there the actual type of. In this case, F8 is stack use after scope. Again, F8. See this one, stack use after scope. I'm going to show more examples. So how would a function like is bad? Because I showed this function. If shadow byte is bad, report and crash the application. So how would that look like? Again, this function will check if that memory location, the input, is actually in poison memory. So it will do the calculation I showed earlier to get the, so the offset is the location of shadow region in memory. See the same formula I showed earlier, right? So it will get the user address shifted at the location in shadow memory as an offset, and then check, okay, if it's 0, then it's in legal memory. If it's different than 0, and it means it's one of the flags. Again, I'm going to link it back to here. So 0 means addressable memory. See the zeros here? These are addressable memory in my program. This, what you see here is the map of the shadow memory. This is not your user memory, not your program memory. It's the shadow memory mapping to your user memory. So 0 means addressable memory. FA in red is the poison memory. So 0, you see the zeros, I kept the same colors, right? When in doubt, use colors. So these are F8 and whatever flag is it's used to tag there. So, and 0 is addressable memory. So that's what this function checks. So if after I do the calculation to get the shadow address from the user address, so from the user address, I go to the shadow address. If the shadow address is different than 0, it means it's in the red zone. Doesn't matter what value. The value will be printed in the report. But it's different than 0, so it means it's, in this example, it's F8, let's say, right? So different than 0 means red zone, poison memory. So let's say we have an access here in process memory, right? Is bad, it will map the shadow byte in shadow memory in a 0 zone. So it will give a 0 result, so it's in addressable memory. So then it will not take this conditional, and it will allow storing food into this pointer. So it will allow me to store at this location because it's valid. and I checked in shadow memory. But if I have an address here at the end of my addressable range, so the shadow byte will point into non-zero shadow memory, whatever it's there. Let's say it's F8 in a red zone, and then it will trap here and display the report and crash the application, and I will not get to this instruction of writing bad food. All right, everyone on board so far? So how does it keep track of these kind of things? So that's one of the reasons why it needs to hook these memory allocation routines. A normal routine will try to allocate in sort of contiguous zones, depending on the type of allocator and the memory pressure and fragmentation that you have available. Whereas the Asan instrumentation allocation routine will intentionally space apart allocation units so that it has these gaps between allocations where it can actually poison memory. So it will artificially inflate the address space of your allocations, and it will space apart your allocations, so it can flag in shadow memory, can flag those as red zones, as poison memory. So it does this artificially. And when a block is deallocated, so you see I had the alloc 3, so I had the block 3 here. When a block is deallocated, its corresponding shadow byte is poisoned, and the runtime intentionally delays reclamation of stuff from shadow memory, so that it knows that this was a deallocated object and I cannot write into it and fool the runtime. So it has a sort of clever technique to defer these reclamations, and so it poisons the memory for a deallocated, the shadow memory for a deallocated object there. So that's why you cannot write in something that you just freed there. Let's say block 3. So that's how it detects heap underflow, overflows, use after free, double free, and so on. Okay, I said that already. Okay. For stack, very similar thing, just works a bit differently, but same concept. So it will mark different parts of your stack with different kinds of markers. I gave here some examples: left red zone, mid red zone, right red zone. It has all sorts of conventions of how it flags the different regions of your stack. And in my example here, you see I have 12 bytes there and an integer on the stack. See, and I'm trying to write a 0 in the 13th location of my byte buffer there, and the Asan runtime checks if that address, that offset, you see here there's an offset. So this is, maybe I should use the mouse here. So it checks if this offset, this address is poisoned, and it will trap in the Asan runtime and abort until reaching that instruction. So stack red zones works sort of similar to how the heap works, but they use different kinds of markers. Same concept. Containers are an interesting example, and this was a development that came later in the Asan journey, let's say. Because if we take vector, but it's not the only container that exhibits this, but vector is most used one and maybe most vulnerable to these kinds of exploits, because vector has a capacity and a size. And the problem is that from the point of view of the memory allocator, all the vector capacity is legal memory, because its capacity, its allocated capacity, it's for that vector. So it's from the point of view of the allocator, that's legal location. So I can legally put stuff there. It will not by default trap any Asan runtime. but semantically it's wrong. we putting stuff here outside of the vector bounds, because capacity for a vector is, we have to remember that capacity for a vector is an optimization. Ideally, a vector should have just a size. The reason why it has capacity is that we want to achieve some performance guarantees for geometric growth. We want to have constant time pushback. And so capacity is a technique that we use to geometrically grow a vector, but semantically, we should never consider these parts of the vector, right? We should never be allowed to access things outside the vector size. So conceptually, the yellow stuff there is not part of the vector semantically. And this has, I'm saying that this came later because this required work on the library side. This can no longer be achieved just with a runtime and memory hooking techniques, because it requires that the library participates and opts into these kinds of mechanisms, various different kinds of annotations and techniques. And by the way, you can do that for your own data structures. So if you're implementing custom data structures like that exhibit similar things, you can opt into this mechanism and leverage Asan for your custom containers. There's a very good presentation by Miro Konyep from CPP North this year, writing your own Asan aware containers or something like that. If you, I can look it up and post the link on Discord if you want. So that's a very good presentation, and you can do that for your own containers. I'm not gonna talk about that. I'm gonna mention that all standard library implementations actually have support for this now. And what they do is, again, very similar. You should be used to this by now. Poison memory. So it poisons the remaining capacity of your container, so it can detect access patterns like this. And mind you, you see what I did here? Let me use the mouse because I'm not friendly with the online audience otherwise. I keep forgetting.
It doesn't show the mouse.
Doesn't show the mouse?
It's not nice yet.
I have to maybe move it to the other screen.
Yeah.
Where is the other screen? That's the question.
Yeah, it's
Okay, got it, found it. Okay, so what I did here, if I would do here, you see, if I would do V sub 3 instead of P sub 3, if I would do V sub 3 there on the last line of the code, V sub 3, that kind of pattern could be detected cleverly in this situation. Because I would be accessing using directly the vector. But as soon as I do any kind of aliasing, like I do here, where I take this pointer to point to the beginning of the vector, and then I do P sub 3, then only a tool like an address sanitizer can detect this kind of access and detect container overflow.
2 questions.
Yeah.
First, why use the get pointer to and zeros element if you can just use the data method of stud vector?
Just my personal preference.
Sounds horrible. Well, but
I'm old-fashioned.
But
Sorry?
It's UB in some cases.
Of course it is. If the vector doesn't have elements, it's not legal.
Yeah. Well, another question which is more important: what happens if you assign something into P3?
If I what?
Assign
Into
P index 3.
Same thing. Same thing.
Even on assignment, you realize that the
Yeah,
memory is
yes,
poisoned
yes.
in a way that shouldn't work even with assignment.
Yes.
Because in some cases, well, if you
but only because that remaining capacity is poisoned.
Yeah, I understand.
Otherwise, it wouldn't work because that's valid memory.
Yeah, but I mean, sometimes some memory is uninitialized, but could be validly written too. which
Yeah.
which needs a different type of poison.
In this situation, I would say Asan tries to detect a correctness issue. It's not a memory safety issue because that memory belongs to the vector. It's not a problem that you write in that location. That memory rightfully belongs to the vector, so you could write on it.
I understand.
But semantically is wrong. Like bad things will happen.
Yeah, I understand, but my question was like whether there is like it detects if it has the right kind of poison that prevents this. Because
what do you mean by the right kind?
Well, for example, if you create an integer and don't initialize it, it's an uninitialized variable which should be poisoned, and you can write into it, but you cannot read from it. And
yeah,
so you basically need a different poison for this situation than.
Asan doesn't handle uninitialized variables like in general. But if you're using an uninitialized, as you mentioned this a few minutes earlier, using an overflow variable or an uninitialized variable to index into something else or to do something like that, then yeah, it will detect those kinds of scenarios.
Yeah, if you go just a little bit over the edge, like the typical kind of +1 error. How is it called? That's not. Yeah, just you know what we're talking about.
Off by 1 error.
Yeah, off by 1 error.
Yeah.
Then
it's not always plus.
It will surely detect this, but yeah, but I understand that if you just craft the right number that would just overflow it in the right way, then yeah, no way to detect that.
Yeah, and also if you're doing stuff at the beginning, if maybe you were thinking about that, there's
More poison.
things there's things in shadow memory before that allocation.
Yeah, but that's related to the allocation thing, not about the vector.
Yeah, it's not specific to the vector. Question?
Yeah, so actually, this is like a source of false positives if you use Asan, because if you instrument only part of your binary and your vector uses the intrinsics for the poison of the container, then actually like your call size will disagree. They will be combined into like different things. And then one, it's IFNDR, and two, it will false positive.
That's the same problem of using different it's different implementations of the standard library in different modules and trying to mix them together. Same kind of issue. It's a different implementation, right?
I mean, yes, that's why it's IFNDR and TB, but also like you have said that there is like zero false positives in other sanitizer, and you can use it regularly, like instrument only part of your code. This is applies where you can't.
If you're sharing that vector, if you're between the two parts, if you're sharing that vector between the two parts, yes, exactly. If you have the same vector shared across maybe a function boundary or something from different translation units, that one is instrumented and one it's not. Yeah, that situation is bad. Yeah, and that's not the only situation, by the way. There are many other situations where you can get weird things if you're not doing the whole thing with Asan.
Not necessarily. If all the instrumented functions are hidden in like library implementation, if they are not templated, and you link with the library which use the instrumented values, the instrumented functions, and it should work.
If you're using a DLL, then no.
Sorry?
If you're using a DLL, for example, if you're calling a function that it's exported or something, you can get into situations where it won't be. It won't be what you expect. Yeah. So it's sure when you're doing these kinds of gradual adoption and interop, sometimes you'll hit weird situations. What I'm saying is that it's worth it. Yeah, you will hit some weird situations, and ideally, yeah, you should be able to compile your whole thing with Asan, ideally, but sometimes you cannot. Maybe you have some problems, some limitations, but ideally you should try to do everything. And even if you cannot do it, like even what I'm saying is that it's worth the pain, even if you're doing gradual instrumentation, even then it's worth it, because sure, you will run into like some weird situation like the ones that were mentioned, but most of the times you will run into actual bugs that you need to address. Like that's the benefit. And sometimes you will hit a weird limitation, and okay, you'll move on, or you'll compile one more DLL or one more part of your program and say, okay, let me get past this and maybe see if I can instrument more of my application. Sure, I'm idealizing here. I know I've gone through pains of trying to adopt this, but I'm saying it's worth it because you uncover a lot of stuff, and I would say that pain to reward is worth it. Like you will get some pain, but the rewards are worth it. Question?
Can you go back to the analog slide?
Which one?
Couple of slides back, I think.
Wrong way. Wait.
Yeah. No. I mean,
Forward?
Forward.
Yep.
Forward. So, how do you get right that delay reduced? So how can you guarantee that whatever would be done after that piece of memory is reused was referring to a different context and not to the context that you would like to monitor anymore? I mean, I'm curious about how to get that delay right before you get that memory back to green for the allocator.
I don't know the detail.
Okay.
What I do know is that the shadow memory remains poisoned, but I don't know when it is actually reclaimed. I mean, when it's flagged. I'm assuming when surrounding allocations go away, there's some logic to figure out what was zombie regions when the surrounding allocations are reclaimed. But I don't know the details in the runtime, how it works.
Yeah, there are multiple strategies, but usually you just keep going until you run out of like next place and you go back. Or if you
like a free list kind of thing.
If you are feeling more anxious, you just go free list.
I suspect it so, but I don't know the details, so I'm not gonna assume it's how it's done. But I suspect that's the kind of thing that it can be done, like a free list kind of thing. But I don't know the details here. Okay, where were we? Yeah, here. So
wait, stop. One more question.
which slide?
No, regarding the previous ones, but I didn't know whether you would mention it or not.
Yeah.
Turns out you won't. So my question is, does it also insert this kind of poison between elements in an array? Not array, between into object layouts?
What do you mean, padding?
Yeah, like padding, or maybe
yes.
when you put stud array and an integer behind it.
Yes.
And if you
it knows about padding in your structures.
But I mean, padding isn't the only problem. You might have you might just put
alignment. You mean the alignment?
No. I mean, I put a stud array that and an integer just behind it, so that there is no padding between that, nothing. And I do an off by one error, and from this array I would hit this integer.
It knows that those things are different entities, different fields in your structure.
Yeah, and if I put another stud array just behind it,
it's the same thing as if you put two integers in a structure. It knows that you have two integers there in the structure. It doesn't assume that it's a twice as large integer. You know what I mean?
Well, not really.
So it knows that you have. Let me go to this, maybe the stack picture I had. Yeah, this one. So it knows the stuff you have on a stack. Imagine it's similar to if you would have a structure here.
Mm-hmm.
Like this could be a struct that you define.
Yeah.
So, question?
But when you have struct, the constraint inside the red zone because it would alter the struct layout, which it cannot because the translation in it would be incompatible with the uninstrumented one.
You definitely couldn't share that structure from two translation units for sure. It would have different size. Yeah.
Yeah, so
Yeah.
it is not the same as the stack because
Yeah. You're right. In a structure, yeah, it would change the size of the structure, and you could even because in a structure it's legal to offset inside that structure.
Yeah, so
Okay.
this is complex, but
So yeah, it's different. It's the stack situation is different than a structure.
It used to be, and I don't know whether it ever like the past prototyping, but if the structure had constructors and destructors, it would insert basically the red zones into it, change the alignment of the object and so on, because it's assumed to be complex object and you can't really like
If it's not an aggregate.
Anyway.
If it's not an aggregate, yeah.
Mod, which doesn't exist, but if it's mod, then it doesn't. And it can detect this. And the idea was that you could use like Intel's NPX to detect this. And I don't know if it has ever made any progress past that.
Me neither. Don't know.
I can imagine it could alter the dynamic constructor, but which allocates, but not the.
You aren't supposed to share the structure between TUs anyway, because that's just like info NDR because you have violated the non-definition rule and whatever the hell happens.
Static struct. It's constrained to one TU.
You have to instrument it in all TUs.
Yes.
Like every TU that uses the struct and sees it should have the same status whether you have Asan enabled or not. And then like every time the compiler will make the same decision, right? Make the same alignment adjustments, and so it works.
Okay.
Because it is the same layout.
Well, I doubt that actually address sanitizer modifies layout, even non-standard layout stands.
Ew. Jeez. That's undefined behavior. I doubt that as well. Yeah. I that's why I agreed with his observation that it's not the same situation. The struct and the stack, it's not the same situation. So I doubt that structs are affected by this.
This just leads me to a possible little problem that if you just develop your code with Asan, then there can be one possible issue that it could cause you, and that is that if you are trying to hash an object and you just take its size and run murmur on the whole object or some other hashing function,
yeah,
then if there is no padding, it's fine. If there is padding, you can get garbage inside of your object, which will be read by the hashing function, and you will get inconsistent hashes of instances that should be semantically identical.
Yeah, but you get what you asked for. Like you build a hash based on what's in the memory. Like
if you do this, if you make this mistake without Asan, you'll start getting errors. If you use Asan, you will not get an error because the memory poison will always be the same. And
but isn't there some way to detect if you're reading padding instead of actual values?
Yeah, but you can. You're reading.
I don't get it.
It's in shadow memory, not in the actual.
Exactly,
memory.
it's not in the actual memory.
So
if you're never gonna read those F8s and whatever I showed there.
So what is inside of padding of an object there isn't any poison?
No, that's why we said that we agree that the structure is not
well,
affected.
But that wouldn't alter the layout. It's padding that would be there.
Yeah, I don't think it works like that.
Okay.
Yeah, and even if it did, you would never read that byte because that's shadow memory. You when you read, you only read your process memory. You can never read shadow memory.
And if I, but
You
like
directly,
this,
I mean.
these usual hashing functions would cast it to 8-byte integer. And in that case, they would read a bit of valid data and shadow memory, and I don't think this would be detected.
Shadow memory is not near your memory.
Yeah, but this
It's
poison.
the thing that I showed here there with the diagrams are just conceptual.
Yeah,
Like
I meant padding, not padding. Isn't shadow memory, or what is it then? What?
padding is padding.
So basically, if you overflow,
The shadow memory is not physically next to your actual memory. It's just how you calculate the locations, the addresses.
Yeah, but in that case, the place between I don't know. I put a short integer and a long integer after each other, and there will be a lot of padding. And if I make a mistake and access this padding, then it won't notice this problem.
On a stack, you mean?
No, inside some struct.
I don't think it affects the struct. That's what I'm saying.
Okay, so it will not find the problem that I have, I don't know, an array of two 16-bit integers and a 64-bit integer afterwards that get padded with 4 bytes. And if I overflow this one array with off by one error, it won't find it.
But how are you referencing that thing in your structure?
Let's say I put a stud array with 2 elements, and I accidentally access the third one. I'm just trying to speculate what's done in the padding.
Yeah, now I understand what you mean, but I don't know. I don't know what happens.
On the GitHub, it's address sanitizer intra-object overflow, and it doesn't detect it. So the example they put here is you have a struct S that has int buffer of 5 elements, and then it has another integer.
That's what he said, yeah.
Yeah, and then if you do S, if you have a pointer to S, then you use
use the offset, yeah.
the offset, and the offset is 5, it will not detect. So
yeah, that's what he said. So it's not covered by this.
Yeah, so it's, well, it wasn't covered anymore. This is actually from 2015, so maybe it was fixed in the meantime.
I don't think so.
But yeah, it will be detected by Intel NPX.
Yeah. I never played with that. Okay. Remember, where was I? I'm almost done anyway. So yeah, I think this is where I left. So the instrumentation is very fast comparatively to other tools. Average slowdown in instrumented program is usually around 2x. Of course, it depends on the type of workload and so on. Some problems and stuff you need to know. So I showed this a few times when I said I showed that snippet, like if is shadow memory poisoned, Asan report, and I said it traps and crashes your application. And the whole idea is to not allow those writes and not allow the process to be in the zombie state, like take it down immediately. So usually this is called one and done, like first problem, abort, report it and abort. So I've shown this snippet a bunch of times today. Problem is that when you have really large test cases where you have hours and hours of builds or hundreds of thousands of tests and distributed machines and so on, this is not really usable. If it aborts at the first thing it will find, of course it will find something. There's no code base that doesn't yield any results in Asan. So unlikely. So at the first problem where it will hit this, if it will just abort, it's not very practical because you have to look at the report, you have to address it, make a patch, make a PR, submit it, PR, CI pipeline, wait another day. So it's not very practical. And a solution, which is a fairly recent development, is continue on error, which is a policy for ASAN. And this unlocks a new workflow to use ASAN as a memory safe checked build, where you build this as you build the debug builds as a way of a flavor of your builds. And as the name implies, it will return control back to the application after reporting every error. It does some magic things inside. There's a bunch of things that have been reworked to avoid the LLVM symbolizer, and how to integrate the ASAN runtime with the application runtime and so on, and avoid clobbering that happens on the ASAN internals when you continue. And of course, representing unique errors in the error reporting. So it required a lot of internal changes. But as the name implies, it's just a simple of it's a configuration flag, by the way. So instead of aborting the application, it will just collect all these reports and let the application continue as if it was not trapped under ASAN. And this way you get your cumulative report, and you can address in bulk many of them. So it's a productivity boost. And of course, this unlocked a lot. This came later, but unlocked. I would say this really unlocked the potential of ASAN, because for many projects and teams, ASAN was okay. It's a nice tool, but in practical terms, I cannot really use it. And continue on error actually unlocked using it at scale. And for the winter theme event, and that's why I said warm fuzzy feelings, the idea is to combine them. I said that from the beginning. Combine sanitizers with fuzzing. This is where the power comes from. Of course, not using a fuzzer, and if you have good test units and you're exercising your application, that's all also good. Like, don't assume that just because you don't doing any fuzzing, you're not going to get out anything out of it. You're going to get a lot out of it. But with fuzzing, you can get way more. And we talked a bit about fuzzing before. So I would say this unlocks a new workflow where you can have this as regular parts of your CI builds, where you compile with the ASAN runtime, you run your tests, your fuzzing, but whatever, and you get the reports, you fix the issues, and you continue. This can be a part of your development loop. Warning here is that some overly enthusiastic people actually build things with ASAN and think they can ship stuff with ASAN. Because they say, okay, I'm building the instrumented application, it runs fast enough, it meets my performance requirements. I'm going to ship it because it's safer to ship it, because it will crash when something happens, and it will not allow any exploits. So problem is that it's even worse, because ASAN is a pretty predictable instrumentation technique, and memory exploitation can identify ASAN instrumented binaries, and they're even easier to exploit, because you have like a big red targets around, and the instrumented binary has very predictable layouts and memory patterns. So it's a very bad idea. Just I wanted to mention that just in case anyone gets overly enthusiastic.
Question.
And it's just a second. It's not a joke. Like, when ASAN became popular, people actually did that before they realized that this is a bad idea. It took a while.
That's a huge warning not to do this.
And now, but some people thought that was a good idea, because looks like it's like a checked build. It's strong.
Oh, but what if I never give the executable to anybody and run it only on my servers?
If your servers are in a vacuum, isolated from the world, then
Well,
sure.
I assume that those that can access my server can be trusted.
Is your server doing any I/O?
Well, but
Is any I/O reaching your process?
Well,
If your
in that
process
case,
doesn't do I/O, it just heats up your CPU.
yeah, but they
has no outcome, aside from heat.
Well, but I mean that somebody would reach it, but only through some general protocol, and
That is perfect.
That's still useful.
As a perfect parser and protocol implementation. No, if as soon as you have input for your application, you are vulnerable.
So how would that kind of exploit work? Do you mean that like I
I'm not a hacker. I don't know.
I mean, I would do fast test as just as a client to find where it crashes and get some idea that okay, here it crashes, so I'll try to play around it and try to go over the end of the poisoned area. And
sure, I'm not a hacker. I don't know.
Yeah, that regardless, you don't want to just have more possibilities to crash your thing running on a server in general, because that is itself a vulnerability. You can just crash more. It's just bad.
Yeah, and also if it's like a service, it means it's long lived, and that also exposes a lot of memory issues. Usually short lived. For example, you could say like a compiler, for example, is a perfect example of a crappy implementation, because it can be as crappy as it can be, because it usually exits quickly. Like it can leak memory, it can be unsafe. A compiler can do all sorts of crappy things. It's a short-lived process.
You
hopefully.
also trust all input that is put into it because you are intending to run it afterwards, and
yeah,
it's
so
much easier to hack your PC by running something that you compiled than by using a bug in the compiler.
yeah. All software has bugs, and if your software does any kind of if your software is doing any kind of I/O, any kind of observable effect other than heating up the CPU, then you are vulnerable.
Well, and if I like don't crash it when something happens, just have it printed. Is there a way that somebody could detect it, like some malicious user client?
Probably. You saw that big list I showed at the beginning. Somebody does that,
I was just thinking about like this option, like let's say I have a lot of instances of a server, and sometimes swap one instance with one with Asan, observe what it does for a while, and then swap it back just to collect some data.
You could do that. I don't know what you would achieve with it, but no, I don't know. What I would say that so if you're interested in memory exploitation, there's good presentations on that. I'm not a good person to speak about that on memory exploitation, but there are plenty of well-known techniques that are explained, and usually software tools protects against those because they're already well known. Things like ROP are covered by stuff like control flow guard and XFG and all sorts of cookies and things that secure code gen toolchains actually know about the most popular exploitation techniques. But there are plenty more techniques that are not yet well known. and tools will not protect you against those. And that's why you need to work on building more trust in the code you generate. You just say stuff.
The shadow regions in the structs, and yes, it actually still ends up extrapolating.